Hey y'all, it's Mr. Virus, and we are going to go through, I'm going to talk about the two FRQs that were assigned this week. Now before I go through and do the solutions and talk about those, I do just want to say that if you didn't get all of these completely done, that is totally okay, and do not feel bad about not being able to get them done. Because in order to, and I kind of said this in our Zoom meeting as well, in order to really fully go through a unit like this, and we've been through some parts of it, like the electric fields and potential and electric potential energy, but especially the capacitance is new. So to fully learn that and then be able to fully complete an FRQ based off that, we're trying to do this as quickly as we can, given the short amount of time that we have to go through some of this electricity and magnetism stuff. So if you find yourself either feeling bad that you didn't get as much as you wanted done, or if you're doing 5, 6, 7 hours or a lot of time into this, either way, I would say don't stress yourself out or overwork yourself on this. Do what you can, and I'm going to go ahead and go through and just talk through the solutions to these. But again, don't feel bad if yours doesn't exactly match up with everything that we go through here. All right, so the first question says that there's a figure shown with 4 charges at the corner of a square. The square has side length s. So we've got 2 positive charges on the top, 2 negative charges on the bottom. All the sides of the square are s. There are 5 questions. What is the total electric potential energy of the array of fixed charges? What is the electric field at the center? What is the electric potential at the center? Sketch the portion of the equipotential surface that lies in the plane of the figure passing through the center. So that's just asking where is the point at which, at every point on a line, your electric potential is 0. So that's equipotential. It's a line or a plane in which all points on that line or plane are a 0 or the equal same amount of electric potential. And lastly, how much work would the electric field perform if you moved from the midpoint of the right side to the midpoint of the top? So we're going from here to here and looking at how much work the electric field would perform on a charge. All right, so I'm going to move over to the solution and talk through this. And go back a couple times to refer to some things as we go through it. So for the first one, I'll just scoot this down a little bit so that hopefully you can see a bit better. All right, for part A, labeling the 4 charges. Now where they get this at the top here, this UE, so this is our electric potential energy, and keep in mind we want to separate the concepts of electric potential energy, which is an energy, symbolized by U, and the electric potential, V, or voltage. Those are 2 different things. One is measured in joules and is an energy. The other is electric potential, measured in volts or voltage. So this one is our electric potential energy, U subscript E. And where they get this, if we go back here, when they were first looking at electric potential energy, this is earlier in the chapter. They're looking at changes in electric potential energy equal to the work done. So they're looking, and if you have 2 Qs, so you'd have big Q, little q, you can define the change in potential energy by going from one point to another by this equation. So 1 over 4 pi times epsilon naught. Epsilon naught is the permittivity of free space. It's a constant that is used for a variety of things. And if you remember in class, I mentioned one time, or a couple times I think, that this whole thing here, 1 over 4 pi times epsilon naught, that's just the K constant that we got from Coulomb's law. So anytime you see 1 over 4 pi times epsilon naught, that is just K 9.0 times 10 to the 9th with all its crazy units. All right, so when we're looking at change in potential energy, they did this through change in potential energy equals the work done by an electric field. There's 2 charges Q. There's, again, your K constant showing up, and then moving a distance from position RB to RA. Okay, So if you have any two charges, so here they're calling them Q1, Q2. If you have any two charges, the potential energy at any given point. So this was a change in potential energy by moving an object. This equation here is just saying if you have two charges separated by any distance r, when you move them, you get a change in potential energy. If you're just sitting there with two charges, the potential energy, electric potential energy between those two charges is K times Q1, Q2 over R, where R is the distance between them. So in our problem, we don't care about this upper part because we're not having a change in potential energy. We are not moving those charges. This is just a potential energy that exists due to the fact that those charges are affecting one another. So based off that, every pair of charges is going to interact with each other. So the 1 and 4, 1 and 2, 1 and 3, 3 and 4, 3 and 2, 2 and 4. So there's going to be 6 combinations of charges that are going to interact and affect the total electric potential energy. So that's why they say the total electric potential energy, UE, is this K value times the sum of all the possible combinations of Q. So here we have Q1, Q2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4. And these R's are just going to be the distances between all of those. So the distance between 1 and 2 is S. The distance between 1 and 3 is, that's the one that shows up here, S times square root of 2. Just do some Pythagorean theorem to find that horizontal or diagonal distance. So 4 of the distances are S around the sides of the square, and then 2 of the distances between the charges at the corners are S times square root of 2. So combining all those together, and based off the fact that each of these charges is either positive or negative Q, so they're putting those in, it'll either give you a positive Q squared or a negative Q squared when you take the two charges times each other, depending on which two you're talking about. So they're going to do this, sum everything together and add it all up, and then multiply it by the K value, or 1 over 4 pi epsilon naught. And when they do that, we get this thing, which they kind of simplify over here. So negative square root of 2 divided by 4 pi epsilon naught Q squared over S. So this is just taking each combination of two charges and factoring in its contribution to the total electric potential energy, and then summing them up and multiplying it by the K value. All right, for part B, we're looking at the electric field in the center. Now, the important thing to notice here is that I like to imagine in the center, if you had an electron, what would happen to the electron? Due to the electric field, the charges Q1 and Q3, one would push that electron diagonally down this way, and 3 would also push that electron diagonally down this way. Because the positive charge is pushing it away on this diagonal line, the negative charge is attracting it down this way along that diagonal line. Likewise, for charges 2 and 4, the electron would be pushed downwards away diagonally from this positive charge. Oh wait, oops, I just totally said it backwards. The electron would be going this way, and it would be attracted to the positive, pushed away from the negative. Totally mixed that up. But the way that we draw electric fields, anytime that you have a positive charge and a negative charge, the electric field lines are always going to go away from the positive and towards the negative. And that's why all these arrows are going to be pointing downwards. So the electric field from 2 and 4, these ones here, are both in the same direction. That electron would respond based off those fields in the same way, but they're both pointing towards this negative, away from the positive towards the negative. Same thing here, we've got the electric field from 1 and the electric field from 3, both pointing this way. So because all these charges Q are the same exact amount, those electric fields are going to be equal in strength. This point is equidistant from all of these charges, so the electric fields in magnitude are going to be exactly the same. And because of that, the horizontal components, E4 and E2, are going to cancel with the horizontal components of E1 and E3. So there's ultimately no net horizontal electric field in this configuration because we've got Q2 and 4 going to the left, Q1 and 3 going to the right. but we do have a net downwards force. So there's an angle of 45 degrees between all of these electric fields, 1, 2, 3, and 4, and this net electric field downwards. So the total is 4 times any one of them. It could be E1, E2, E3, E4, any of them would work, times the cosine of 45 degrees. So we get 4 times the K value times Q over R. This is that distance R here. So it's 1/2 of that S times square root of 2. So it's half the total diagonal distance across. That is the distance from any charge to that point in the center. So this is just KQ over R. That's our electric field E1. So KQ over R squared times the cosine of 45 degrees times 4, because there are 4 downward electric field components from each of these. The downward part of 2, 4, 3, and 1 are all helping to contribute to the total or net electric field. So each one of these charges is going to contribute a downward portion of its electric field to the total. All right. Now we're looking at electric potential or voltage V, measured in volts. The potential at the center of the square is going to be 0. Now, when we're doing this, similar to what we did with the other things, we figured out, or we need to count in the contribution from each individual charge Q. And when we do that, the total voltage is just K Q over R. So that's our voltage is KQ over R, and we have to do it for each individual charge. So this QI, the sum of charges Q over R, the radius R, for the total number of charges, which is 4. So we have K times Q1, Q2, Q3, and Q4. And the distances are just R1, R2, R3, and R4. They're all, again, from the corner to the center, it's that same distance, 1/2 S times square root of 2. And what we find is when we do that, we put in the positive charges for these two, the negative charges for these two, and they actually all cancel out. So the potential at the center of the square is 0. There's a non-zero electric field at the center of the square, but the electric potential at the center of the square is 0. All right, so we're looking for now an equipotential line. At every point on that line, we want V to equal 0, just like it does at the center of the square. So what we're going to look at is, if we do that, this equipotential line on the center of the square, everywhere on that line, we need this to be 0. So no matter what these two charges are, let's say 1 and 4 here. So 1 and 4 have the same charge, magnitude of charge, positive Q and negative Q. And at any point on the horizontal line through the center, the distance R1 and R4 are going to be equal. Likewise, at any point on this line, the distances R2 and R3 are going to be equal. So a horizontal line through the center is a place at which, or a line or plane on which the voltage is going to remain 0 no matter where you are, because the positive contribution from this Q and the negative contribution from this Q are always going to be equal amounts, and on opposite sides, opposite signs. So the voltage is going to remain 0 at all points on that line straight through the middle. So that's what they're asking for an equipotential line, is where is a line or plane on which the contributions to voltage from all the charges involved are always going to remain at a total of 0. All right, and the last part for this one, we're asking for the work done as we're displacing from point A to point B, which is right on the right side, middle of the right side, to the middle of the top. So the work done by the electric force is given by the equation negative Q times delta V. And that's also earlier in the chapter talking about work done by an electric force. We can look at the change in voltage times the charge Q for whatever charge. So the little q is just this charge that's being moved from here to here. So it's like a test charge, or a charge that we're using. It's not one of the 4 charges on the corners. just to clarify that. All right, so it's given by this equation. Now we know that on this equipotential line, anywhere through the middle, the voltage is 0. So this delta V, or delta change in electric potential, change in voltage, at point A, that is 0. VA equals 0 because it's on the equipotential line. So really we just have to deal with VB. And what we do for the voltage at B is we do K, Q over R, and we need to do the contributions from all of those charges on the corners. So when we do that, we get negative Q, and this is negative Q times K, and then all those 4 charges, we have Q1, Q2, Q3, and Q4, and the distances are, for Q1, we get 1/2 S, because this distance R1 from that charge to the point at B is 1/2 of S, where S is the length of the side. Same thing for number 2. Charge 2 has a distance 1/2 S, and these ones are a little weird to figure out, but it's going to be a right triangle where one side is S, one side is 1/2 S, so it's the square root of S squared plus 1/2 S squared, which will be, when you add those two together. Now both of these are the negative Q's, so you've got your 2 negative Q's at a distance square root of S squared plus 1/2 S squared. That's these lines, the diagonal ones. And when you add those together, you get negative 2Q over 5, square root of 5 halves S. And then these two together, we get 4Q over S. So it's kind of just a lot of algebra and solving through. Really all we need to do is say that work equals the negative charge times the voltage, and when we do that by taking all the individual components, adding them all up for each charge, we get through all this stuff. So long process, and then you get to this. So they're simplifying. Yeah, so there seems to be quite a bit of algebraic simplifying in there. I'm not going to go through the whole thing in the interest of time here, but you have it there. So if you need the answer, it is there. Okay, I'm just going to move on to capacitance. Okay, so the main thing with capacitance is I picture a battery when I think of a capacitor. A battery is a capacitor. It's just 2 plates or 2 locations where on one you want to keep all the positive charges, on the other you want to keep all the negative charges, so that any electron in this case that's interacting with those 2 plates or 2 sides is going to respond a certain way based off all the positive charges being in one spot, all the negative charges being in another. And that's what a battery is. You've got your positive and negative side, and then you get the electrons to flow through a wire or whatever you're doing with it whenever you connect the 2 sides. All right, in this case, we have what's called a parallel plate capacitor. So we've got these 2 plates, one on either side, and I'll go to the question. So figure below shows a parallel plate capacitor. Each rectangular plate has length L, width W, separated by a distance D. We're going to have a few questions. Determine the capacitance. And then an electron, mass m, charged negative E, is shot horizontally into the space between them with an initial velocity of v0. It just barely misses the top end of the top plate as it exits. This picture here, it's shot with v0, goes up, barely misses the top of the top plate right there. In the diagram, sketch the electric field vector when it's halfway down at L over 2, and then sketch the electric force vector at the same position. Determine the strength of the electric field between the plates in terms of L, D, M, E, and V0, E being the charge of the electron, and determine the charge on the top plate. All right, so again, this is newer stuff, so if you got some of it, great. Don't feel like you needed to get all of it. All right, so capacitance. The definition of capacitance is just the broadest definition is that it is the charge per potential. So Q over V. And for parallel plate capacitors, if you go back into the chapter, I can flip back there quickly here. So if we go to capacitance, one second, gotta flip through. potential cylinder, there we go. So capacitance. The most broad definition here, just what I said, charge per voltage, ratio of Q to V, Q over V. For a parallel plate capacitor, that's going to be epsilon naught, the permittivity of free space. That should be on your equation sheet, I believe, times the area of one of the plates divided by d, the distance between them. So in our case, that simplifies to the capacitance is area epsilon naught times area over d. These plates are rectangular, area is length times width, so the capacitance is epsilon naught LW divided by d. All right, now we need our electric field vector and our force vector. Now, we know that the electron is attracted upwards because it almost hits the top plate as it's exiting. If the electron is going towards that, the top plate has to be the one that has all the positive. So the positive plate is on top, the negative plate is on the bottom. Based off that, we can draw the direction of the electric field knowing that if this is the positive plate up here and this is the negative down here, the electric field vector always points, and the electric field lines always point away from positive towards negative. So we can draw our electric field with a downwards arrow from the particle or the charge, the electron at that point. So there's our electron halfway at 1/2 L, and the electric field vector is pointing down. For C, we know just, they said C explanation and illustration, because it is attracted upwards. The positive plate is up here, so the force that's attracting it upwards is, well, pulling upwards. So the force on this electron causing it to take that path is a force Fe directed upwards. So those two are fairly straightforward as far as just understanding that based off the path of the electron, which plate is positive, which is negative, how do we draw the electric field and the force vector based off that knowledge? Part D. All right, so the main tricky thing here is they're asking us to write our answer in terms of L, D, M, E, and V naught. E is the charge of the electron, no problem there. We've been dealing with charge all the way along. M is the mass of the electron, which for us is a little weird because, let's put it over here so we can see these. So M is the mass of the electron. That's a little weird. We haven't been using mass a lot in this electricity stuff. Now L, D, and V naught, those are all lengths or distances and an initial velocity. And that's all stuff from kinematics. So what they're asking you to do in part D is go back and connect your knowledge of kinematics and even forces, because we have a mass here and that's going to come in with forces. So we're going back to kinematics and forces, and we're going to connect that into what's going on here. So we have an initial velocity, V naught, as we're shooting this electron into this space, and it takes that curved path upwards. And we know that based off the fact that there's Fe, this electric force that's pulling on it the whole time, it will be a constant force because we have a constant electric field. So it's not going to pull stronger at these different points. So determine the strength of the electric field between the plates. So the acceleration of this electron is just Fe over m. And Fe is Q times E. That is from the equation for electric field. So E equals Fe over Q. And if we rearrange that, we get the force, the electric force, is equal to Q times E. All right, so using Newton's second law, saying acceleration is force divided by mass, the acceleration of the electron is equal to QE over m. And the charge Q of the electron is that charge E, vertically upward. Yep, so the acceleration is in the same direction as the force. It's accelerating vertically upward. Now, going back to our motion unit, our kinematics, we're going to use, we can look at the displacement. We know that the displacement vertically is delta y is just 1/2 of d. So we're gonna bring that in a little bit, and we know that delta y is equal to v naught times t plus 1/2 ayt squared. So the initial, now this is important, the initial velocity in the y direction, keep in mind that we are shooting our electron horizontally in between these plates. There is no initial velocity in the y direction. And so that's why we're using all the force, all the acceleration. This is almost weirdly like a projectile motion problem, because there is no horizontal acceleration. we're assuming no air resistance, and there's nothing that's attracting or pulling or applying a force in the horizontal direction. The electric field and the force from that electric field is only in the vertical direction. So our acceleration here is an AY due to this force. There's no horizontal acceleration. So we're going to say that the initial velocity in the y direction is just 0. It's all horizontal as we shoot the electron horizontally into that space, and then it accelerates upwards in the y direction based off this force Fe. So we put in what we had. Acceleration here equals q, or E times E over m, E times E over m. So we put that in 1/2 at squared, 1/2, that's our acceleration, times time squared. All right, so again, yep, notice that the x direction remains constant, no horizontal acceleration. We can also quick put in if there's a constant horizontal velocity, that horizontal velocity v naught has to equal the length L divided by time. So v naught equals L over t, or t equals L over v naught. That's just saying that the time it takes to go the entire distance horizontally is dividing that distance L, or that displacement L, by the v naught x, because our x velocity does not change the whole time. Okay, so now putting that back in here, we're putting in all kinds of things. So delta y is just 1/2 d, because we go from shooting it out here in the middle horizontally, and then it goes all the way up to the top. So the y displacement is 1/2 of d, so we get d over 2, and then we get 1/2 times that acceleration that we had, big E times little e divided by m, and then we're substituting in for time that L over v naught squared. So this is all the variables we were looking for: L, D, M, E, and v naught. So we know that the equation that we had for kinematics gives us all this. Now we're going to solve it for electric field E, because that is what we're asked to do, determine the strength of the electric field between the plates. So it's just algebra, rearranging all these crazy variables, and it ends up being E equals dm v naught squared over little e times L squared. All right, part E, it's asking us to determine the charge on the top plate. So we're going to go and take this, we're going to take this. Now there's two key things here. One of them is that in order to get charge, we can use capacitance, which we already have from our very first question. We found the capacitance is equal to epsilon naught times LW divided by D. And we can get charge if we take, capacitance is charge divided by voltage. So charge is capacitance times voltage by the definition. We know the capacitance and already have it, so really all we need to get is the voltage. Now we know that the change in voltage, so the charge on the top plate, the change in voltage is equal to E times D. So that would be the electric field. Yeah, so our change in voltage, and that's looking at the distance d. So there's an amount of voltage or electric potential that you would have at this point, and then there's an amount of electric potential you would have at this point. And we can find that delta V by saying delta V equals E times D. So really all we're doing is we're taking this electric field value that we had from part C, or yes, D, part D. We're taking the electric field value we had from part D and multiplying it by the vertical distance d to find the change in electric potential. So that change in electric potential is going to go into this equation in order to give us the charge on the top plate. Because we're finding the difference between this delta V is just the change in electric potential from the top plate to the bottom plate. So this is the strength of the electric field in between the two plates times that distance, vertical distance d. And when it's pretty much very similar to this, we just multiplied it by d, so it's d squared instead of d up here. And then all we have to do to finish this out Q equals that delta V, which we had right here, and we multiply it times the capacitance. So we take this whole thing right here and multiply it by our answer from part A, which gives us epsilon naught LW over D, and there's a lot of stuff going on here, but a couple things cancel out. The the L cancels with an L squared, D cancels with a D squared, and we get epsilon times the width times the D distance, vertical height, times mass, times V naught squared divided by the charge of the electron and the length of the plates. Okay, and lastly, we are asked to find how much potential energy is stored in the capacitor. Now, if in the chapter there was a part where it talked about potential energy for a capacitor, and if we look at this, I mean, we're used to kinetic energies being 1/2 mv squared, but it kind of looks like a kinetic energy, 1/2 times this squared. So back in the chapter on capacitance, it talks about the electric potential energy, and it defines that as 1/2 C delta V squared, where C is capacitance, delta V is the change in voltage or electric potential. So going ahead and putting that in, we have all these things. Again, it's the same. We have delta V from here, we have capacitance from here, so we just put them in. 1/2 times the answer from part A times this delta V that we got in part E, put them in. Again, ton of variables, ton of things being squared and cubed all over the place. Some things will cancel out, and we get this sort of monstrosity for the electric potential energy. So it's really just taking this equation, which for capacitors, obviously this will only work for capacitors because there's a capacitance in there, but this is an equation for electric potential energy for a capacitor. And that is found in the chapter in the part about capacitance. And that is it. So that was a lot of stuff, a lot of crazy electricity capacitance deal. So if you have more questions, I'll always be happy to do a Zoom call or answer them however I can. So let me know for sure, and thank you for watching.